Hi, welcome to my presentation. I'm Jeevan Vemulapalli and I shall be taking you through a small presentation on my proposed topic, image segmentation and a gesture-based feature recognition system. This project is based for image processing and computer vision for fall 2016 at the University of Florida. Through the course of this project, we propose an enhanced version of segmentation based on implementing static heuristic methods. So this is the overview of the project. In the initial phases, we discuss the basic essence of what image segmentation and gesture recognition are, their applications, related work, and the problem statements specific to this project. We discuss specific heuristics that have helped us achieve improvements in results in the efficiency of obtained images. We've adopted these experimental results for methods in test cases and the algorithm further on. So, firstly, let us talk about image segmentation and gesture recognition systems. Images come in a multitude of types and mixtures to become the visual that they are to us. They can be classified and categorized into various forms of classes depending on their attributes. These components can be differentiated among many factors, among some of which are region-based and color-based. Therefore, image segmentation is a process that helps us achieve millions of applications, a primary application of which is in gesture recognition itself. Gesture recognition is something that most of us know today and see in almost all electronic applications. These can be used for many autonomous applications in our daily lives. We can use simple gestures to interact with a multitude of devices without having any physical contact with these devices. There are some critical fields such as sign language interpretation where this is highly important. These are some of the common detection methods that we have used or seen in this field of work. Color, feature, and region-based detection are among the most common techniques. However, these have been improvised over time with the following techniques listed below and have helped us achieve a much more efficient segmentation process. So, let us take a look at the problem statement. Now that we've discussed the basic essence of image segmentation and the varied reasons and factors that it could be dependent on, we will realize that there's a mammoth solution space that has to be covered. It is understandable having an idea of the number and size of pixels in the image, isolated or neighboring when one target area is undergoing certain processes. So in view of this, the problem statement for our project proposal is the need of an optimal use of efficient heuristics to solve the problem of such a vast solution space. The general heuristics utilized are hill climbing and simulated annealing, while we have also proposed the use of taboo search in further applications. So, let us have a look at what each of these three are and how they differ from each other. Speaking about hill climbing is the fastest heuristic among these applications. However, this comes at the expense of quality as hill climbing is only factoring in local maxima. So in solution spaces that are vast where global maxima are required, hill climbing is not useful. This is a resultant in extremely suboptimal solutions if many peaks exist, which is common in many applications and is therefore suitable only for small solution spaces. Hill climbing gets stuck at all peaks except its neighboring elemental peaks, and therefore it's only useful for local maxima. This allows it to work very fast. On the other hand, simulated annealing can find near optimal solutions by escaping these local maxima and continually gathering a global maxima variable at any point of time. It has the capacity to reach down to a lower value than an optimal solution at that point to be able to reach out to a global maxima further down the path. It's very sensitive to its input parameters and therefore must be configured well to get good results. The analogy of simulated annealing can be defined in terms of image size and attributes and the elemental nature of being isolated or neighboring, while in hill climbing they have to be only neighboring elements. While simulated annealing and taboo search have pretty similar applications, taboo search is faster and works well for most problems, having updated the local and global storage combined together. This helps it to achieve a higher rate of efficiency while working with the same optimal response as simulated annealing. So the adopted methods for the test cases in this project are color-based, feature-based detection, differential projection between the fore and backgrounds, mean shift and cam shift, morphology-based transforms such as erosion dilation, opening and closure, and filtering technique analysis with heuristic modeling. Speaking of the data path, this is how we've initialized the algorithm for the peak process. Now, in the first box, we can see that there's a predefined image or starting a video uplink if we are capturing a live image. And then we capture the gesture based on the background and foreground and subtracting both the images. We have initialized variables at preset constants equal to 0, because of which we can ensure that these will not interfere with any change if we're taking any live images. We mark a circular contour which will act as the point of reference to all edges and color-based image segmentations henceforth. We find the fixed points distance, which becomes the maxima from this circular contour point, and compare the distances with the maximum boundary segmentations to get position marks of our peak points. At the end of it all, the number of peak points are stored with a feature count that gives us the number of features and helps us to identify the number of points. These peaks will eventually lead to a feature count that is identical to the feature that we provide on the camera. So let us have a look at the first part of it, which is the contour matching. On the left is the original image upload. Now in this image, if we were to take a small selection such as what is shown under user defined region, which is the yellow component, the tool based on the algorithm we have given gives us a match between the color range based on the mean values that it has obtained on the delta E. On the right side, we have seen a match and non-match images which have shown us the mean value of 16.3. This is also a similar image where we have uploaded another image taken from our camera in University of Florida. We have defined a small segment of the image, and here we have seen that the delta match is 14. It's important to keep in mind these values as we will obtain an important result from them henceforth. We will now discuss the procedure of how these images reach the delta E and mean values. So let us capture an image that is on our phone or on the laptop. Now this image that is captured undergo these 4 transforms as shown on the right. These 3 transforms ensure that all the essentials are covered, and we then proceed to defining a certain aspect of the image that we want segmented based on its color. So the amplified delta E mean is shown on the right of the user defined region we have chosen ourselves. Now we can see an image called dark mark hotspot. What this defines is that among the user defined region, when it has been amplified, the part of the image that is most closest to the color and the contour of that aspect of the image will become the darkest part in the dark mark hotspot. So the darker an substantial area is, it means that it has matched the image more strongly than the rest of the image. From this we get a match, and the dark mark hotspot gives us a range of delta E, which helps us define the characteristics obtained in this image. So now, if you had seen previously, we have seen a change in the mean values of 16 to 14, and now it's 7.5. This is directly in correlation to the amount of contour that is available in each of these images along with its colorization. The more the colorization and the contour is, the higher the delta E value also is. We will now discuss how we can target the peak point identification. Let us consider an original background as shown on the slide. Then let us capture a gesture, which in this case it is the number 5. The center palm identification indicator is the roundness initialization that we give in the code. This has to be calculated, which depends on each feature and each gesture that we make. None of these are static. Now, this center palm identification indicator becomes the point of reference for every reference node and distance taken henceforth. How you can see right now is the boundary set condition marking along the structure of our hand, which has been the gesture and the image segmentation from the background of this image. Based on edge tracking and color segmentation techniques, we can see that the tip of our fingers are the maximum distance from the center point, which we have captured earlier, and this is therefore the maximum distance before the segmentation flag is enabled along any single node. This is now done on all 5 edges, where in the algorithm it has been mentioned that every node which is recursively the longest distance from the center point becomes the edge node, and these become all the peaks. So now we can count these n holes, which indicate that each reference node has become a single peak on its own. So the number of nodes become the number of peaks, which in this case, as we can see, is 5. So we have the original image and the user input gesture on the right, and in step 1 we discussed the center point reference node, which acts henceforth as static to all reference distances taken henceforth. Step 3 outlines the shape of the gesture that we've provided, and step 4 denotes all maximum distances to gather the peak points. Now in step 5 the peak points have been captured in respect to the reference nodes that have been identified in step 4. Now if we were to look at the image, on the right you could see the design of the peak points, which is captured by the tool for final peak point capture in response to the input gesture we have provided. First, it reads the first peak point, number 1, and correspondingly till the number of peak points get completely read. So we have 1, 2, 3, 4, and 5. Now that all the nodes have been counted, the reference point is now considered to be done, and the number of peaks is finalized as 5, which helps us to identify our figure as number 5. So, in conclusion, through the course of this project, the author has implemented detection and segmentation techniques and has conducted experimental analysis using multiple heuristics for the solution space of the methodology's applications. Now, it has been found that for small solution spaces where there are very minute differential nodes in the image attributes, hill climbing is found to be more suitable. In most real-life scenarios, which is otherwise, taboo search, due to its ability to hold memory in its resulting local and global maxima, provides a more balanced technique and produces results of higher accuracy. Now, although this project deals with real-time capturing and not real-time computing, we could extend tracking performance to meet constraints faced in the continual capture of real-time feed, where there's a lot more necessity for resource allocations as well as signals. Secondly, with regards to the tools that we use, it would be better if we could decrease the mean time frame between the point of input and output capture. In short, this is the whole time which the specific hardware could be used instead of the software tools that we use presently. This will make it more efficient, but would cause an increase in resource allocation and also the cost function. So it is critical to strive for a balanced trade-off and choose these applications depending on the level of necessity that we need. With this project, We could add a machine learning network to train the feature recognition automatically but not detect additional improvisations. It would be a vital and feasible extension at a more advanced level application of this technology. Online template matching could also be another future extension that could be added so that it all can be read in a live frame. Now, let us look at this final image. We can notice that at the small elemental nodes, we have that hill climbing is at its highest peak in comparison with simulated annealing and taboo search. This is because at those elemental nodes, it's a very small solution space and the heuristic multitude therefore goes high because of its capability to cover all nodes in a much quicker time than the other two. As we increase the elemental node count from point of initialization, we see that simulated annealing and taboo search take off because now they provide much more efficient vast resources within the same time frame used for all three heuristics. Taboo search minutely beats out simulated annealing at these points as well because of its ability to maintain and store both the local and global maxima. So it's important that we understand and the usage of taboo search in high level applications where there is a need of vast resources but of limited efficiency. So the taboo search helps to solve that problem because in such cases the amount of resource allocations is anyway high and therefore does not get exploited, while at the same time it does provide us with a much more accurate representation than simulated annealing. This concludes the project, and if you have any details, please contact me and I could send you a project report which could discuss further if you're interested in this area. Thank you.